que va a estar dando su charla de Introduction to Beacon Object Files in the Context of Red Teaming Operation. Fuerte el aplauso.
Thank you. Hello, hello. So, okay. So today we'll be talking about the introduction to beacon object files in the context of red teaming operations. Before I start with my presentation, I just wanted to say a few words about me. That is, my name is Rafael Felix. I go by the nickname of Biscoito. I'm a red team operator / malware developer at Hakai Offensive Security. And I have about 4 to 5 years of experience with malware analysis and malware development. And actually, I just wanted to say a few words about that. That is, malware analysis is such a cool thing to do. You actually get to learn more about the operating system. You get to learn about more low-level programming. And it's just fun in general, since you don't know what the malware is actually doing. So it's kind of like a puzzle where you don't know what it's doing, and you need to discover what the malware is doing. And malware development is also so cool, since you get to learn more about evasion techniques and how they can be used in real-world cases. And there's my LinkedIn, my GitHub, and my research, one of which we'll be talking about today, which is Coffee. That is a COFF loader made in Rust. So here's a little bit of the summary. We'll be talking about what is a BOF, how does a BOF look like, how are BOFs executed, alongside with a live explanation of Coffee's flow of execution and code. And we are going to develop a BOF from scratch. So we can show an example code for a BOF. How can BOFs be used? Coffee executing who am I, Coffee being used as a library, and that they come with limitless possibilities. So you may ask, what is a BOF after all? BOFs are short for beacon object files. They are basically just just object files compiled from GCC that contains only raw code, only machine code in this case. And it can be used alongside with a COFF loader, which is the common object file format used to load that machine code that gets compiled from GCC. Or any other compiler you want to compile a object file. BOFs are also OPSEC-friendly from a design perspective. So they are very small. They only contain the code that is being used. And in the loading process, we just load the code and we free it so the process gets back to normal. So that's very cool. Custom functions can be implemented in the loader, so the BOFs functionality can be extended. So we can implement custom functions in the Beacon API, so we can extend the BOFs functionality. So this is how a BOF looks like. Here we have the code example that does a simple hello world. We can see that we call the entry point go, with the name go. We pass the arguments, we pass the length to those arguments, and then we call 2 functions here, which are implemented in the beacon compatibility layer header, which contains all the API functions for our BOF. So in that file, we have all the API functions for our BOF, which is basically just an object file with extended functions, in this case being our beacon API. So here we call beacon output and beacon printf. Beacon output just outputs a string with its length here. So we see we are outputting hello world from beacon output, and in beacon printf, we output a string, but formatted as we are calling printf. So here we see hello world with the string passed here from beacon printf. And you may ask, how can we compile that respective code? And I show you here. Here is an example using MinJW32 GCC, which we can compile an object file by passing the -c argument into the GCC command here. So I'm compiling for x86, and we are outputting our code to this demo.x64.0 object file. And then we can execute the compiled code, this compiled code here, with our coffee tool, which is a COFF loader. And here we can see it is doing all the allocation for all the sections, resolving all the internal imports, which are beacon output and beacon printf. And we process all the relocations, we write them, and then we call the entry point here, and we get the result, which is hello world from beacon output and hello world from beacon printf. So I'm going to show you that process of loading our BOF a bit more in depth. So here, how are BOFs executed? The following is a flowchart showing the execution process of our coffee loader. But the process varies from loader to loader, but the process is almost the same. It's similar from loader to loader. For example, we have COFF loader from TrustedSec, which is also another beacon object file loader that is made in C. But in this case, with Coffee, we are using Rust. So, starting in the flowchart here, we pass the file, which is demo.x64.0 that I showed you guys before, which is just a simple print on the console to test it out. So first we pass the file, then we parse the COFF file header using Goblin. This is a very important part because we are using Rust. So with Rust, we have some libraries to use, which are very interesting. And one of them is Goblin, which is a library that implements all the COFF header that we can use way simpler. Otherwise, if you're implementing your own COFF specification in your Rust code, you can look up the PE format website here from Microsoft, where we can read out the structures, out the documentation, the functions that need to be used, so we can parse our COFF header, and that's it. So continuing on the flowchart, we parse the COFF file, then we parse through the number of the sections present in the COFF file. So every object file we have sections, just like a normal PE file in Windows. Every object file has those sections, that being .text, .rdata, and the list goes on. So in each section, we get the section size and we allocate the memory with the respective section size. So for example, we are parsing through the .text section. And the .text section has, for example, let's say 100 bytes, just for example. And then we virtual lock, we call the virtual lock syscall for Windows, and we allocate the memory with that size with virtual lock. So we allocate the memory for the section size, and then we push each section's allocated base address to a vector that we are going to use later. So after that, we check if the section has data. So if it has data, then it is initialized. So we just perform a simple mem copy with the content of the section inside our COFF specification, and then we copy that to the previously allocated memory. So that means that we allocated memory with this section size, and now that virtual memory has the section data for our object file. So you guys can see where are we going with this. We are just relocating all the code in our object file to our memory, and then we can parse everything and execute it. So after that, we get the COFF header sections and iterate through each again. We check if the number of relocations is greater than 0, and iterate through the section's relocations. So in each section, we are going to check if that respective section has relocations. So if it has relocations, we then parse through those relocations. And then continuing, in each relocation, we get the symbol at their respective relocation table index. The relocation table index contains all the relocation data inside our COFF header. In this case, it is the index to that relocation table, as we can see here. So continuing, with the symbol, we get the name of that symbol from the string table. So with the name of that symbol, we can check if we are using an internal function or we are using an external function, in this case, parsing an external function. So if we are parsing an internal function, in this case, as I've shown you before in our code here, for example, this is an internal function. As we can see here in the header file, we pass declaration specification import, which is just a C macro that extends to DLL import. So we store these functions in the storage class of our object file, and then we parse them using this symbol from the relocation table index. So we check if the symbol's name is internal, so if the symbol's name is inside a list of our internal functions, we know that symbol is internal. So we can parse it respectively in our Rust code that I will show you later on this presentation. But basically, it's just passing a pointer to our own defined Rust function as a extern C. But you may ask, what if it is an external function? If it is an external function, we are talking about a Windows syscall here, in this case. So, for example, we are calling, let's say, getUsername A, which is the Windows API function that gets the current username present in the Windows system. So if we are calling that, we need to first load library, the library we are using, so we can get the address of the library we are using inside the running process. So for example, getUsername A is present in the advanced API 32.dll, which is the library that this function is exported in the Windows system. So with that, we get the address of the loaded library here, calling load library. And then with the address, we can get the procedure address of our WinAPI function using the syscall or the WinAPI function getProcAddress with the function name. So in this case, let's say we are parsing through getUsername A. Our loader will get that external import, and will load library with the name of the advanced API 32.dll, and then we'll get the procedure address of that respective function with getProc address. So now that we have the addresses of our internal and external functions, we can start writing our relocation using unaligned write and read with Rust, of course. So we get the address of our import addresses, so internal and external, and then we write that to the memory. By doing that, we are relocating the memory present on our object file, which is machine code, to the memory on the loader, which is runtime code. So then we parse through all the symbols once again, and we correlate them with the string table. And by doing that, we can get the symbols, every symbol name once again, and we check if the symbol name is the entry point name. So, for example, we are using Go as an entry point name, which is just a function in our C code. And with that, we get the Go symbol, and with that symbol, we can get its value, which is just an offset to the actual function. So, for example, in this case here, we find the Go, and the symbol value is 74. We sum it up with the doctext section base address, and we get the address of our entry point. So with that, we just need to cast the address to an actual function. In this case, in Rust, we use transmute to convert it, to cast it to a function, the address to a function, and then we can just call that function in Rust. So we are programming in C, we're making a beacon object file in C, and we can just call the function after parsing all the object file and the machine code in our Rust loader, and we can just call it as nothing has happened, which is so cool. So, so then the beacon object file gets executed, and then we can see the output in the console, which I've shown you guys here. We get the output here. After calling the entry point, we get the entry point name, which is Go, and we get its address, and we call it, and we get the output. And you may say, oh, that's so cool. How can I use it? Nowadays, some C2 frameworks already come with with their respective execute BOF command. For example, some examples here. Obviously, Cobalt Strike, which they made the beacon API, which we use nowadays. So Cobalt Strike uses beacon inline execute, which is their own beacon pack thingy. We have Sliver, which has the implementation of trusted sex COFF loader. We have Havoc too, which has C-Spider's implementation of the COFF loader, which is Coffee loader. We have Parse C2, which uses Netitude's run OF. And we have Metasploit here, which recently implemented trusted sex COFF loader. So here I have an example of Sliver running the situational awareness who am I BOF here. And what's interesting in this, you see here the Sliver command line. One thing that is so awesome about BOFs is that we can extend the functionality of our execution without adding any other functions in our C2. For example, in Mythic C2, you can create an agent by adding every single type there. So, for example, I want to execute assembly. I want to execute the shell. With BOFs, you just need to enable the BOF functionality and then we can just run BOFs on the way. So we can just have the BOF functionality enabled on our agent, and we can just execute any code we want with just one functionality in our C2 framework enabled. So that comes in handy when we want to make stealthy operations, when we want to OPSEC. That's very useful to use beacon object files, since we don't need to enable any other C2 functionality, just our execution of BOFs. So that's it. Here I have a simple example of our coffee loader executing the situational awareness with my BOF. So you can see we run the executable-b, which then we pass the path to our beacon object file, and then we get the output of the execution, which is all the information about our user. What's very interesting about Coffee is that it was made to be implemented in other Rust projects too. So if you have a Rust project which you want to include Coffee, you just need to cargo add coffee/LDR, and you can import here our Coffee. We pass the BOF as an array of bytes, so that's cool. So we can download the BOF from anywhere we want. So if you want to pass the BOF through DNS communication, pass the BOF through any other communication, and then we get the array of bytes of that BOF, and we execute it here. In this case, as whoami doesn't have any arguments, we just pass none here, and we get the execution in our stdot. So I wanted to show a little example by making a BOF here live that basically just gets the current user, and we can execute it using Coffee. So let's open here. Can you put my screen here? Hello, guys. Can you put my notebook screen? Just wanted to show my screen.
Ya. Marce, ¿qué tienes en tu pantalla? Ah, porque tiene el segundo monitor.
Yeah.
To duplicate your screen. You see this?
Okay, great. Awesome.
Great.
So here we have the example.zip file, which we will compile using GCC. I'll just show, oh, it's, okay, let's see if it changes back. So I'll just code a simple beacon object file. So first we start by including our beacon.h file, which is the compatibility layer of our beacon API. So here we can see that file. It is importing all the functions from the beacon API, which is Cobalt Strike's beacon API. So we see we have some interesting functions here, such as obviously the printf. We have some other functions here too, like inject to processes. We have we spawn processes, and actually what's very cool about that, about the Beacon API is that we can just write another function here if we want. For example, we can write my function, do something, and then we can implement the function inside our coffee code, which is present here. I'll open on Visual Studio Code. Here, in our beacon API.rs, we have all the implementation for all those functions. So for example, with beacon printf, I'll show you guys. Here, we pass, as we've seen with the BOF example, we pass the format and the arguments, which is the VA list that we then parse as with printf compatibility, and then we output that respective code, that respective output in our stdout. So here, all we need to implement a new function is just add a new Rust function as extern C, and then my function do something here. And then we call that function from our beacon object file, and it's going to work like a charm, which is very nice. So let's continue with our implementation of our beacon object file. So first, we need to include, obviously, the beacon API for our compatibility layer from Cobalt Strike, and then we make the entry point as ushar. So we pass the arguments here. We pass the length as ulong, and then we include our windows.h, which contains everything Windows related, and also those types here. So with just that code, we can just, for example, do a beacon printf, calling with callback output, and then the contents, so hello world, hello Ekoparty, 2023. And to compile that beacon object file, everything we need to do is just go here in our folder and call x86, 64, mingw32, gcc with the -c to our example, and then output it to example.x64.0. So we have the compilation of our beacon object file, and we can load it using coffee here by calling cargo run -b with the path of our EcoBOF example.x64.0. So we can see here that we have the hello Ekoparty 2023, and we get the output to that respective function. So if we call as verbose, we can see everything that the loader is doing. It is allocating the memory for the section. It is processing all the relocations for each section. It's going to get the symbol name and the symbol name for internal and external functions in this case. So here we can see, and then we call the entry point as with the address here. Awesome. So, and you may ask, how can we do something a little bit more complex here? For example, I want to call a WinAPI syscall. I want to call a Windows API function, and I show you. I'm just going to get the get username specification here from our code, and then here I have an example of a Windows API syscall that is going to be loaded in our COFF loader. So we have declaration specification, DLL import. So we tell the compiler to export, to actually leave as an import, that function in this case being get username A. And then we separate the library with the syscall name with a $sign. So here we have the advanced API 32.dll, without a DLL in this case, and get username A, which is our Windows function, alongside with 2 arguments, which is from the function specification. So then to get the username, we need to pass a buffer to our username. And we can do max path, which is the max path for our username, +1 to include the new terminating string, and then the length here, which is size of the buffer username. So then we call the syscall, which is advanced API 32 get username A, by passing buffer username and the length as reference, and then we can beacon printf here with callback output username string with our buffer username. And then we can compile that to see if we actually get our username by executing our BOF. So let's see. Oh. Oh, and size off, okay. So we compile. Oh, the length. Yeah, sorry. So we can compile that BOF, and then we go to our coffee here, and we can execute it here. So we can see we get the execution. We get our, it's actually a little small, let's, here. So we have the execution here, hello Ekoparty 2023, and we get my username in my computer, which is Biscoito. So yeah, here's a little example of a beacon object file we made here. So we just print and we get the username, and that's it. So coming back to the talk itself. So I've shown you how it can be implemented as a library. And now, lastly, I just wanted to say how they come with limitless possibilities. So BOFs are easy to develop, as you've seen. All you need is a Win32C compiler. Development is fast. Since you don't need to mess with project settings, you just need to write a little C code there, and we can compile that. So it's very easy to develop a beacon object file. BOFs are very, very small, which can make a big difference if there is bandwidth limitations in your operation. Sometimes there is, so that's important to tell. And that one of the heaviest BOFs on one of the biggest repositories that contains BOFs, which is TrustedSec CS Situational Awareness BOF, weighs about 23 kilobytes in file size. So that's really small, since it only contains machine code for our beacon, for our object file. So instead of chaining up external post-exploitation tooling and rely on advanced OPSEC techniques like process injection and exploiting memory, BOFs run inside of the running process, and its memory can be changed within the allocated addresses. And as I've shown you, new functionality can be implemented in the coffee/beacon API.rs file and changed in the beacon compatibility layer header file. So you can just, for example, you want to do something different with our system. You want to implement a more advanced process injection technique or process hauling, for example. You can implement that in the beacon API and add it to the beacon compatibility layer header file. And there's also the possibility to implement other ways of getting the procedure address of function names, like implementing your own getproc address. For those who develop malware, you probably know there are plenty of custom implementations of either load library or getproc address, and you can do that in the loader's code too to make it even more stealthy. So what I've shown you is that we can compile a small code made in C that gets run in our Rust code, and that code can be very flexible. So for example, as I've said before, we have a C2 framework which has only the beacon object file execution enabled, and we can just pass any beacon object file that does anything in this system to execute and be happy. So that's it. Thank you so much. If you have any questions, any critics, any questions, something? You're awesome. Thank you.
¿Alguna pregunta? Bueno, no hay nada. Les damos las gracias. Otra vez renovamos el aplauso.